So this is a three-phase half-wave controlled rectifier. You can see that the controlled rectifier. This is a three-phase controlled rectifier. Means three thyristors are connected across the three-phase supply. Each phase is denoted by phase A, phase B, and phase C. And here the thyristor are connected. Suppose in phase A it is thyristor T1 connected. In phase B it is T3 and phase C T5. So three thyristors are connected at three phase of the three phase supply. And here the R load is considered. Okay, so half wave controlled rectifier. So here when T1 is on means it will be in the forward blocking state, and it will start from this state. This is our conduction sequence diagram. That is the three phase supply. This is the phase diagram. That is each phase the supply is given like this. So you can see in this three phase diagram that since T1 is connected with A phase, it is starting from the point 30 degree. In the previous day, we have studied about how to draw the phasor diagram for these cases. Okay, similarly, in this case also, the same way the phasor diagrams are drawn, and it is a controlled rectifier. So here you can see this is phase A, the signal for phase A. This is the signal for phase B, and it is the phase C. So the A phase is starting from 30 degree. Before 30 degree, it is not touching zero axis, and there it is continuous. So T1 is on from 30 degree to 150 degree. That means each phase will be in conduction up to 120 degree. That is 30 degree plus 120 degree, 150 degree. So 30 degree to 150 degree, T1 thyristor is on. So the if I draw a conduction sequence diagram, we will get this portion. Okay. So let us. So from this you can see that the from 30 degree to 150 degree T1 thyristor is on. So T1 is on from, this is the conduction sequence diagram. So T1 is on from 30 degree to 150 degree, and then again VB. VB means it is connected with T3. So T3 is on from 150 degree to again 150 plus 120. That means 270 degree. Up to 270 degree, this T3 is on. So this way the conduction diagram is drawn, and this is when triggering angle alpha is equal to 0, it is starting from 30 degree. When the triggering angle is 0, it is starting from 30 degree. Before 30 degree, it is not touching zero axis, and there it is continuous conduction. Okay. Mm, Before 30 degree, it is continuous conduction, and after 30-degree firing angle denotes the discontinuity. Suppose firing angle is 15-degree, then the conduction will start from 30-degree plus 15-degree, that is 45-degree, and your diagram will be like that. Suppose this is one diagram. In this case also, uh, this is suppose a shift, and if it is a 30-degree, if it is 30-degree, then 30-degree plus 15-degree, from there your conduction will start, and this portion will be discontinuous, because at when the alpha firing angle was 0-degree, then in this half wave three phase control rectifier, it is starting the start it is starting its conduction from 30-degree. Now if firing angle is increased to 15-degree, then it will after this 30-degree it will be discontinuous, and the diagram will be like that. This way. Okay, so this is for alpha equal to 15-degree. Uh, for three-phase half-wave rectifier for a resistive load, the discontinuous conduction is achieved when alpha is less than 30-degree. Discontinuous conduction alpha is equal to or greater than 30-degree. So when it is at 30-degree, the conduction is like that. That is alpha when equal to 0-degree. Then you will get these types of conduction. But when it is alpha equal to 15-degree, it will be shifted. This is the voltage diagram. This way it will be shifted. That is, this is 30-degree. If it is 15-degree, if it is so if it is 15-degree like this portion, so it will start from this side, and this way it will be continuous. Now if alpha equal to 30-degree, then it will start at alpha plus 30-degree, that is 30-degree plus alpha 30-degree equal to 60-degree. So it will start its conduction from 60-degree. There will be some jump and then it will be continuous. At 60-degree it will jump up to certain point, and then certain point means at 60-degree you can see this is at 60-degree. So your conduction will be like that. This way it will conduct, and it will conduct up to 180-degree. 60 plus 120, 180-degree. This way it will conduct. Now when it is alpha equal to suppose 60-degree, then 30 plus 60 will be 90-degree. So that time what we see that 90-degree is at that point. So 90-degree means uh, you can see that this VC, C phase voltage is coming to 0 point at 60-degree. So this is the negative portion of the signal. So that time, if since it is resistive load, so continuous conduction we will not get. So this portion will be discontinuous, so it is discontinuous during that time, and then again it will start conducting. This is for 90 degree. So if it is if alpha is 60 degree, then we are getting mm, discontinuous signal. So we can get two types of voltage diagram. One is continuous, that is up to 60 degree we will uh, a firing angle before 60 degree, or up to 30 degree we will get continuous conduction and if it is more than 30 degree, if the firing angle is more than 30 degree, then we will get discontinuous. Okay, so uh, for continuous conduction, for obtaining the for continuous conduction, we need to keep our firing angle less than 30 degree or up to 30 degree. So this is above 30 degree. Here the firing angle is greater than 30 degree. Okay, so this way we can get the value. Now if it is RL load, and then when alpha is more than 30 degree, inductor will release energy in this discontinuous portion. Since it is R load, when it is R load, you will get this discontinuity of above 30 degree firing angle. But in case of RL load, it will release the energy stored in the L in the negative half cycle also. So that time it will be the continuous conduction of voltage. So voltage diagram you can get this way. So the voltage diagram for RL load will be this, because it is allowing the negative half cycle also. Okay, so this portion is actually the freewheeling action area, that is 30 degree plus alpha, 30 degree plus alpha to 150 degree plus alpha. So if it is 60 degree, 60 degree to 180 degree, this 180 degree is definitely 150 degree plus alpha. So two average voltage we can get, that is alpha less than 30 degree and alpha greater than 30 degree. Okay. This is the average voltage. Okay, so R load, average output voltage, two average voltage, alpha less than 30 degree, that is continuous, and alpha greater than 30 degree, that is discontinuous. So output voltage, average voltage will be equal to 1 by 2 pi by 3. 1 by 2 pi by 3, 1 by total time, how much time it is conducting, that is 2 pi by 3. 2 pi by 3 means uh, that is 120 degree. 120 degree is our conduction sequence. So 1 by 2 pi by 3, that is 120 degrees, considering as the total time of conduction. So 1 by 2 pi by 3, that should be equal to 3 by 2 pi, and the conduction is from 30 degree, since it is starting from 30 degree, from starting 30 degree it is starting 30 degree plus alpha. When alpha equal to 0, it is like that. This is our diagram. Now from 30 plus alpha, 30 plus alpha to 150 plus alpha, because if alpha equal to 0, 30 plus 120 equal to 150. So that is actually the conduction period, time period. Maximum voltage here Vmp sin omega t d omega t. So we can take common Vmp and get minus cos omega t. This is our limit. Let's put that limit and you will get this value. If alpha equal to 0, then it will be 3 root 3 Vmp by 2 pi. So this is our mm, output voltage or average output voltage of three phase half wave uncontrolled rectifier. Okay. Now when alpha is greater than 30 degree, then also V output will be equal to 3 by 2 pi 130 degree, sorry, 30 degree plus alpha to 180 degree, because the conduction you can see in this case that it is from 30 plus alpha to 180 degree, because after 180 degree it is passing through the negative half cycle, and negative half cycle is not allowed for our load, and so it is discontinuous after that. So we will not consider those portions, and the conduction period we will consider from 30 degree plus alpha to 180 degree, and from that we'll get this value of average voltage. Okay, this is for RL load, sorry, R load for two cases. One is continuous conduction, another one is for discontinuous conduction due to the alpha, alpha greater than 30 degree. Now for RL load it is two cases, with and without freewheeling diode. Without freewheeling diode, alpha is less than equal to 30 degree. So 3 by 2 pi 30 degree plus alpha to 150 degree plus alpha Vmp sin omega t d omega t. So you'll get this value. And RL load with freewheeling diode, when alpha is greater than 30 degree, it will be same like this one, 3 Vmp, because after 180 degree with the freewheeling diode, what will happen? With freewheeling diode, we will allow conduction, current conduction, but during the freewheeling action, what is in conduction? That is, diode is in conduction. We are concerned about the thyristor conduction, so our consideration should be up to thyristor conduction time period. So it is definitely from 30 degree plus alpha to 180 degree. After 180 degree to 180 degree plus alpha, during that time diode will act, that is the freewheeling diode. During that time current conduction will be there, but that will not be considered for our average output voltage equation. Okay, so this will be same as R load. Okay. Okay, so three phase full wave converter, this is a diagram of three phase full wave converter. We will now start doing this drawing this one, how to draw the line voltages. Okay, you have to draw like this. you just take 1 centimeter point, sorry, take some points like that. In 1 centimeter difference, you take some points. This way, you take some points. And in between, you take another point there and there. This is the method of drawing line voltages, okay? Okay, take the points like this and add this. Okay, so join the lines like this. And now this is suppose red phase and this is suppose blue phase and so this is another current and that is black. Okay, so this way you just extend this way, just extend it. Suppose this is our black phase, means one of the phase actually. Okay, similarly this is our red phase. It is continuously like this. Okay, So this is our blue phase. So blue phase is like that, this way. Blue phase is continuous. Okay, so this way you have to draw the line diagram. And so suppose this is VCB. This red colored, this one is suppose VCB. This is the line voltage. Suppose this is VAB. And this is VAC. Okay. Next again, this is VBC. And this one is VAB. Next, this one is VAC or VCA. So this way it will continue. Now, what you have to understand that where it is starting. So this is our 0 degree. This is 30 degree. And this way it is 60 degree. This is 90 degree. This way it is 120 degree. So 30 degree, 30 degree, it will go each phase, that is this portion is 30 degree. So this way it will continue. Okay. Now what you have to understand from the circuit, that up to which it is connected. So if I enlarge this, you can understand that this is the diagram, our line voltages. So line voltages are VCB, VAB, VAC, this way it will continue. Now you can see in this picture, this is the three-phase full wave converter. Here the thyristors are connected in this way. At a time, two thyristor will be on. The upper half SCRs are considered as positive group, and the lower half SCRs are considered as negative group SCR, because upper half SCRs are turned on with positive cathode voltage. Okay. So VAB is starting from 0 and VAC is starting from negative value. Okay. So VAB means this one, that is T1, T3 will be connected. So in this diagram, if we can see that VAB, this portion is coming from uh, 60 degree. VAB is starting from 60 degree. VCB, here you can see it is starting from 0, but it is not touching the 0 axis. Okay. So it ends at 60 degree, and from 60 degree it is VAB connected. Now after this 120 degree, VAC is there. So conduction of VAB is from 60 degree to 120 degree. Then from 120 degree to 180 degree, it is VAC. So 60 degree to 180 degree, these two are conducting, VAB and VAC. In this VAB and VAC, which one is common? A phase is common. So the positive half of this cycle for A phase is T1. VAB means T1, T3, and VAC means T1, T5. So this is our conduction sequence diagram, which we will